The next one is loads on columns. Columns carry the live and dead loads from beams and slab and its own self weight. The load may be acting axially and eccentrically based on the type of loading acting on the columns. We may classify them as axial loaded column or centrally or concentrically loaded column PU, denoted as PU. A column subjected to axial load and uniaxial bending PU plus MUX or P plus MUY. A column subjected to axial load and biaxial bending PU plus MUX plus MUY. Slenderness ratio for columns. The slenderness ratio is the ratio of effective length LE to the lateral dimension of the column in that direction. We have two directions on plan and we can have two ratios. You can see the slide. Long side of the column slenderness ratio LEX divided by D, whereas the short side of the column slenderness ratio is LEY divided by B. From IS 456 code clause number 25.3 specify that slenderness limits of the columns as shown in the below. The unsupported length between the end restraint shall not exceed 60 times the level lateral dimensions of a column. If any given plan one end of a column is unstrained, its unstrained length L shall not be exceed 100 B square divided by B, where B equals to width of the cross sectional and D equals to depth of the cross sectional measured in the plane under the consideration. Next is minimum eccentricity. From IS 456-2000 code, clause number 25.4 says that specify that all columns shall be designed for a minimum eccentricity. Equilaterally supported length columns 500 plus slenderness dimensions divided by 30 subjected to a minimum of 20 mm, whereas axial blending considered is sufficient ensure the eccentricity exceeds the minimum about on own axis at a time. Design or a short axial loaded columns. IS 456-2000 clause 39.1 specify that assumptions is the design of compression members. The maximum compression restraint in concrete in axial compression is taken as 0.002. The maximum compression strain at a highly compressed extreme fiber in concrete subjected to axial compression and bending when there is a no tension on this section shall be 0.0035, minimum minus 0.75 times the strain at the list of compressed extreme fiber. In addition, for the following assumptions of flexurals are also required. Plane sections normal to the axis remains plane after bending. The maximum strain in concrete at the outermost compression fiber is taken as 0.0035 in bending. The relationship between the compressive stress distribution in concrete and the strain in concrete may be assumed to be rectangular, trapezoid, parabola or any other shape which results in the predictions of strength in substantial agreement with the results of test. An acceptable stress strain curves is given in IS 456-2000. For a design purpose, the compressive strength of concrete in the structure shall be assumed to be 0.67 times the characteristic strength. The partial safety factor Y of 1.5 shall be applied in addition to this. The tensile strength of the concrete is ignored. The stresses in the reinforcement are derived from the representative stress strain curve for the type of steel is used. Typical curve are given in IS 456-2000 for a design purpose. The partial safety factor is equal to 1.15 shall be applied. IS 456-2000 clause number 39.3 specify that the short axial loaded columns shall be designed for by considering the assumptions given in the 39.1 clause of IS 456-2000 and the minimum eccentricity, where the minimum eccentricity as per clause 25.4 does not exceed 0.05 times the lateral dimensions. The column may be designed by the following equation, that is Pu equals to 0.4 FCK AC plus 0.67 FY AST, where PU axial loaded on the member, FCK characteristic compressive strength of the concrete, AST is the area of longitudinal reinforcement of column, P percentage into gross area of the concrete, that is P into Ag divided by 100. See, percentage of steel P equals to 100 divided by AS divided by AGT. AG is a gross sectional area of concrete B into D, that is a rectangle section it is considered. So A0 is the area of concrete AG minus ASC, AG equals to AG minus P into AG divided by 100 equals to AG into 1 minus P divided by 100. So Fi is the characteristic strength of the compressive reinforcement. The above equation may be rewritten as submitted by AC and ASC values. P equals to 0.4 FCK AG into 1 minus P divided by 100 plus 0.67 Fy P into Ag divided by 100, or we can written as Pu equals to 0.FCK Ag into ASC plus 0.67 FCK into ASC equals to 0.FCK into 0.4 FCK into Ag plus ASC into 0.67 Fy minus 0.4 FCK, a column with a helical reinforcement. The strength of the compressive member with the helical reinforcement satisfy the requirement of clause 39.4.1 shall be taken as 1.05 times the strength of similar members with the laterites. P equals to 1.05 into 0.4 FCK ASC plus 0.61 Fy into ASC, spacing of helical, IS 456-2000 clause number 39.4.1 specify that the ratio of the volume of helical reinforcement to the volume to the core shall not be lesser than VUS divided by VC is lesser than or equals to 0.36 into Ag minus AC minus 1 into FCK into Fy. Considering the diameter of spiral 6 or 8 mm dia at a pitch height S with a clear cover, core diameter equals to DC equals to D minus 2 times the cover. Area of core equal to AC equals to pi into DC square divided by 4 minus AC. Volume of core per pitch height S into VC equals to AC into S. Length of one spiral diameter LS equals to pi into DC minus dias. Volume of one spiral VUS equals to pi into 8 square divided by 4 into LS. See, design of column subjected to combined axial load and uniaxial moment of biaxial moment using SP16 chart. Very important. By here we have to use the SP16 code book. All columns are subjected to some bending as well as axial loads, and they needed to design to restrain both so-called axial loads. Formulas presented in a section 6.7 do taken into account some moments because of include the effects of the small the eccentricities of 0.05 d. When the column subjected to axial loads and moments in one axis, then these columns is said to be under a uniaxial bending. When the column is subjected to axial loads and moments in both x and y axis, then those columns is said to be undertaken by axial bending.